Hello everyone. So this is the second part of our playlist, and in this video we're gonna write a code to demonstrate that with explicit differencing, simulating the temperature profile of a bar with length 20 meters, thermal diffusivity of 1 meter squared over seconds, spatial increment of dx of 1 meters, limits the maximum time step of dt to up to 0.5 seconds. Okay, so first, before going into Python, we have to derive what we're going to do, right? So if we're going to derive the equation, we can just use Python to plug in our equation and solve for it. So in a problem, we are given with a bar of length 20 meters, right? And let's say it has, so the left side of our bar is, so temperature on the left side is going to be equal to the 50 degrees Celsius, right? And the temperature on the right, let's say it's going to be equal to 80 Celsius. And the temperatures in between, let's say they're at 20 degrees Celsius. Okay, because of this thermal diffusivity, the temperatures in between are going to change, right? So we want to plot and simulate how the temperatures are going to change in between. So we're given a thermal diffusivity, which is alpha, right? Of 1 meter squared per second. We're given dx is 1 meter. So dx is the length. If we kind of consider the small steps of the bar, so if we divide bar into 20 parts, so the dx is going to be 1 meter, so that's dx. And the total length of a bar is 20 meters. Okay, so we have to consider the heat diffusion in x direction, right? So using the equation we derived in our first problem, so the heat diffusion equation is derivative of k, derivative of time respect to x, so where is k is a constant of thermal conductivity, plus the heat generation is equal to the rho Cp times the small change in temperature over small change in time, right? Okay, so let's say our k is constant again, because if we wouldn't say that, our problem would be much difficult to solve. Okay, and then let's try to approach this problem. So as we're given alpha, if I rewrite this equation, that's gonna be I can take k out of the parentheses and that's gonna be the second derivative of time respect to x, right? Plus q is equal to rho Cp delta t. So first derivative of temperature respect to time. And let's say we don't have any heat generation, because the heat is going from one position to another. So there's a heat diffusion happening, but we don't have any heat generation. So we're going to say q dot is equal to 0. And if I divide both sides by density times the Cp, that's going to be k over second derivative of temperature respect to x is equal to the first derivative of temperature respect to time. And we know this term right here is equal to alpha, right? So my equation is now going to be alpha times the second derivative of temperature respect to x is equal to the first derivative of temperature respect to time. Okay, So in our bar, let's say we're gonna divide it right into several parts. So let's say we have j. We're gonna mark each number as j, so it's gonna be first, second, third, fourth, fifth, so it's gonna go up to n. And let's say the temperature, so the rate of change of a temperature between two parts are gonna be the temperature. So the first derivative of temperature with respect to x is gonna be the temperature of j plus 1 at n minus temperature at j at n. So let's say our n is going to be, our total time is going to be the n times delta t. Okay? And we're going to divide that by a small change in x. Okay? And so the second derivative of it is going to be, so we're going to assume that the second derivative is equal to the changes of two slopes. So how is that going to be? Over delta x. So that's going to be tj plus 1 minus tj over delta x minus tj minus tj minus 1, which is the one before, the part 1 before, delta x over delta x. So it's going to be the assumption, so we're using explicit differencing, right? So we're going to see if the method we are using is going to work when we're going to plot it. Okay, so that is going to be equal to tj minus 2tj plus 1 minus tj minus 1 over delta x squared. Okay, and for this part, I can say that is equal to the temperature at j at n plus 1 minus temperature at j at a time n over small difference in time, right? So now I can, for this part, I can use this equation, substitute that equation, and for the first derivative of temperature with respect to time, I can substitute this equation. So the equation I'm going to have is going to be the alpha times alpha over the x squared times tj plus 1 minus 2tj minus tj minus 1, right, is equal to, so I'm going to multiply delta t to the left, to both sides, so I'm going to have delta t right here, and for this part I'm going to have the temperature at a point j at time equals n plus 1 minus t at a specific point at n times equal to n. Okay, so let's now consider this whole thing, because we know all of them, right? So we know alpha, we know delta x, and we know delta t. So they're all constants, so let's just replace it with r to make our work easier so that we don't have to work with all of the constants. Okay, and so now I can make this as the subject of our equation. So in that case, I can find out how the temperature at a specific point is changing with respect to time. So if I open the parentheses in the left side, yep, so r tj, if I open it, that's gonna be r tj plus 1 minus 2r tj minus 1 is equal to time at one point at temperature at one point at times equal n minus 1 minus temperature at exactly the same point but at one time before. So I can move this to other side of the equation, and I also have tj, another tj here, right, if I connect them to n. So then I'm gonna have r tj plus 1 at time n minus, that's gonna be 1 minus 2r temperature at point j at times equal to n minus temperature at j minus 1 at times equal to n. And that's going to be the temperature, and that equation is equal to the temperature of j at n plus 1 time. Okay, so now using this equation we derived, we can use the plot line to plot how the temperature is changing and see if actually delta t should be the maximum limit for the delta t. Okay, so now we're going to use Python to simulate the whole situation. So in this part of the video, we're going to write a Python simulation to show that the time step cannot be greater than 0.5, so it shouldn't be stable anymore. So we're going to try to plot the graph and see what is going to happen in cases where dt is greater than 0.5. So as we're going to work with numbers, we'll always start with importing numpy as np, and I thought we're going to use the plot. So from plotly.subplots, we should get import make subplots. Okay, and let's write down what we're given. So we're given the alpha, heat diffusivity, right? Thermal diffusivity, which is equal to 1, right? And we're also given dx, which is also equal to 1, and we're given that dt should not be greater than 0.5. So we're going to see the case where it is equal to 0.5 first, and so we're going to change it to see what's going to happen. Okay, and we know that our r here is equal to the dt times alpha over dx squared. So that's going to be dt times alpha over dx squared. I'm going to run it. Alpha, sorry, typo. No, this is fine. Okay, so we're going to use a list, array list, to show the temperatures at each dx for our bar. So let's say we know that we are dividing it into 20 pieces, right? So that our n is going to be 20. And what we're doing next is we're creating an array for the temperature. We're going to use np full for that. So the temperature, so the number of temperatures in our array should be 20, right? So, and for each one, the initial temperature for, I think this should be the parentheses, yep. And for each temperature, the initial temperature is going to start from T0. Let's say T0, and we're going to specify what T0 is equal to. That's going to be 20 degrees, right? Okay, but, okay, let's specify it before. Okay, but we know that the temperature on the left side and temperature on the right side are not equal to each other. So we're going to say the temperature at the left is equal to, I'm going to say the temperature on the left is equal to 50. And temperature on the right is equal to 80. Okay, and I'm going to say the temperature on the first value of our array. So the Python indexing starts from 0, right? So the first should be equal to the t left, because that's going to be the temperature on the left, right? And the last value in our array, which is going to be -1, should be equal to the t right. Okay, so let's just run it. Okay, now we're gonna change the temperature for several times, right? So for that, we're gonna do a loop for I in range. So we already have the first iteration, right? So we're gonna start from the 1, and we're gonna run it until 0, like until 100, let's say. And now we should include this equation. Okay, so Tj at n is equal to n okay, so we're doing this thing, right? Now we should use the NumPy slicing, array slicing for that. So the temperature is starting from J, right? So the J is right here. So that's going to be the numbers starting from 1 to -1, but it's not going to count the -1. So we're not considering the temperature on the left side and the right side because they're not going to change. So the temperature J is going to be the temperatures in between. So the slicing works that it's going to start from the first value you type and goes until the next value, not including the last value. So these are the temperatures, all the 20 degrees temperatures are going to be equal to R times, so Tj plus 1 to n. So j plus 1. So we're moving one step to the right? So our slicing is going to be, it's going to start now from 2 and go to the end. So that's how we do it in Python slicing, Python array slicing. Minus 1 minus 2 times R times Tj. So that's going to be, again, the temperature from 1 to -1, right? Okay, and minus Tr times Tj at Tj minus 1. So we're going one step to the left. So how that is going to be is, so we're going to consider the temperatures starting from 0 to -2. Okay, so in each iteration, it's going to update our values. Okay, so what I'm going to do now is, so let's create a plot right here. So we're going to make a figure, make subplots, right? And we're going to use figure add scatter. So for x, so we should now determine what we're going to use as x. So for x, we're going to use the number of pieces we have. So which is going to be, we're going to use NumPy arrange. It's going to be the array using n. Oops. NumPy has no attribute arrange. I think, yeah, that was a typo. I wrote, like, I typed 2 R's where I should put only 1. That's going to be x, and in y values, that's going to be our temperature, right? And we're going to make the mode as lines. Modes. It's modes. And we're gonna have a legend for that, right? So for the name, that's gonna be the f string of 0. Okay, because it's our first 0 iteration. Okay, and we're gonna have to add it again, right? Fig add. Okay, let's do that. So we have several iterations, right? But if we plot all the lines, it's gonna be messy, a bit messy. So we're gonna plot some of the iterations. Like, we don't have to plot each iteration, so we're gonna plot some of them. So how we can do that is we're gonna use something called modules. So we're gonna plot each number that is a multiplier of a 10. Let's say that. So if we say it's gonna, maybe let's just gonna do it until 1000, and if I is a multiply of, let's say, 25. So what this gives us is a remainder. So whenever this thing is going to be equal to 0, we're going to plot it, okay? Because if the number can be divided to 25, the remainder is going to be equal to 0, right? So we're going to only consider those points. Okay, so we're going to say fig add scatter x is equal to x. In y we have our updated temperatures. Again, for mode, we're going to have what we're going to have is lines again, and for the name, let's have our I value. Okay, and let's update our figure, update layout. So we want to set the widths to be equal to 800 and height to be equal to, let's say, 600, and template to be equal to plot light dark. Okay, let's try to plot it. So I tried to run it, changing the A to 0.4, and it showed me the plot, and when I plotted it with a dt is equal to 0.5, yeah, it's now working. So the problem I made is, so I had to run it again every time, so that's why I think if I have this x in here, there shouldn't be a problem. Okay, so now let's see. We were saying that our dt, the higher limit for our dt is 0.5, right? Okay, let's see what's gonna happen if we increase it. So let's say you're gonna increase 0.5.8. It's a very minor increase, but let's see what happens. Wow, it looks very beautiful, but it is definitely not a graph. It's definitely not a temperature profile for our bar, right? So now in the next video, we're gonna theoretically prove why the higher limit is 0.5, and then we're gonna use other method which is called Crank-Nicholson to actually find why the error is happening. Thanks for your attention.